This is the first lecture of physical principles of wave energy. I'll start with definition of waves, then we will talk about how ocean waves are generated by wind, we will talk about the difference between natural and design waves, and then we will cover wave parameters and characteristics. So what are waves? A wave is defined as a transfer of energy through the water, and as a result, it causes water to move in circular or orbital motion. Waves are the energy, it's not water, that move along the ocean surface. There are four natural phenomena that are responsible for generation of ocean waves. First, of course, it's wind, which generates waves. Also, lunar and solar gravitational fields cause large waves and tides. In addition, seismic disturbances that cause tsunamis. And finally, disturbances induced by bodies that move near or on the surface. For example, when we have ships moving on the surface, we have waves generated. The main focus in my lectures will be on ocean waves that are generated by wind. Wind waves are mechanical waves that propagate along the interface between water and air. The restoring force is provided by gravity, and therefore these waves are often referred to as gravity waves. As the wind blows, pressure and friction disturb the equilibrium of the water surface and transfer energy from the air to water, forming waves. Because the wind is originally derived from solar energy, the energy in ocean waves can be considered to be as a form of indirect solar energy. Typical solar power of the order of 100 watts per meter square mean value can be transformed into waves with power levels of 100 kilowatts per meter of crest length. And please note that power levels are reported here in different units, so it's not per meter square, it's per meter of crest length. And this is because the nature of waves makes it impossible to refer to power per unit area. We have to consider that waves action takes place throughout the depths of water, and so we consider the power passing through a 1 meter wide slice of water. What are the key mechanisms of wind generating ocean waves? Air flowing over the sea imposes tangential and normal stresses at the water surface, resulting in the formation of waves. Turbulent airflow close to the water surface creates rapidly varying shear stresses and pressure fluctuations. Where these fluctuations are in phase with existing waves, further wave development occurs. And finally, when waves reach a certain size, the wind can exert a stronger force on the upwind side of the wave, causing further growth of waves. Working with waves, engineers work with design waves, because natural and design waves, they are quite different. Naturally occurring sea waves are random, irregular, they have varying wave height and varying wave period, and they are short-crested. These are 3D waves simultaneously coming from a range of directions. And this is how they look like. For engineering design purposes, an engineer thinks in terms of a design wave, which is in contrast to real wave, is of a fixed height and fixed period. And these waves are long crested waves. And this is how design wave look like. So this is the crest length, and these waves have fixed wave height and fixed wave period. For engineering design purposes, the engineers use the simplest propagating wave of unchanging form that is a typical wave and is described as sinusoidal. So it has a form of a mathematical function sine. And this is how mathematical function sine looks like. So y is equal a, which is coefficient, multiplied by sine of argument x. And I show you on this slide a few examples where a is changing from 1 to 2 meters. And you can see that this is the simplest propagating wave of unchanging form, which is a typical wave and described as sinusoidal. This is what engineers use for engineering design purposes. So what are the key parameters an engineer needs to know? Let's consider a schematic diagram to make it easier to define parameters. So on this diagram with the blue line, I show sea surface elevation above still water level. I show still water level with the dashed black line. Coordinate system is defined as x is longitudinal axis and z is vertical axis, and origin is at still water level. Therefore, z, which is vertical axis below still water level, is negative. Direction of flow is from left to right. I also show seabed here and also show two crests on this diagram, and crest is the maximum surface elevation on a sea wave, and trough, which is the minimum surface elevation. So the key parameter is the wavelength, and the wavelength is defined as the distance between two successive crests, in this example between points A and B, or between two successive troughs. Another important parameter is the wave number, and this is defined as 2 pi divided by wavelength. Therefore, wave number, which is k, units for this would be radians divided by meter. Also, wave height, which is defined as the height from trough to crest, or wave amplitude, which is defined as wave height divided by 2, or the distance from still water level to the wave crest. And the water depth is measured from seabed to still water level. So this is the distance from seabed to still water level is defined as water depth, and I use lowercase d to define water depth. In our lectures, we consider gravity waves. So these are the waves whose properties are mainly determined by gravitational forces, and surface tension effects are negligible. Other important parameters is the wave frequency. And wave frequency is defined as the number of wave crests or troughs passing a fixed point, for example point A, each second. So wave frequency units, seconds in power minus 1 or hertz. Also the wave period, and wave period is defined as 1 divided by wave frequency. And this is the time for successive crests or troughs to pass a fixed point A, for example, or the time required for the wave crest at point A to reach point B. Another important parameter is the wave circular frequency, and this is determined as 2 pi divided by wave period, therefore units radians divided by seconds. And of course wave velocity. Wave velocity c is defined as wavelength divided by wave period. And of course we have sea surface elevation above still water level, and this depends on both on position and time. So if x changes and t changes, the sea surface elevation will change. So summary of all wave parameters that engineer needs to know when he designs a wave energy converter. First of all, he needs to know wave height, he needs to know wave amplitude, he needs to know wavelength, he also needs to know wave number, which is 2 pi divided by wavelength. He also needs to know wave period, and usually when you deal with design waves, you know wave height and wave period. Wave frequency, which is 1 divided by wave period, wave circular frequency, or 2 pi divided by wave period, and also wave speed, which is calculated as wavelength divided by wave period. And of course, an engineer needs to know the water depth for the design of his site. No matter what the problem is, an engineer always needs to calculate wavelengths. And how he can do this? Using dispersion equation. We know that the wave velocity c is also known as the phase velocity, because points of the same phase or points with equal surface elevation eta move at this velocity, regardless of the shape of the wave. So if we consider 2 points A and B that have the same surface elevation eta, it means that wave velocity at those points would be the same and as a phase velocity. And phase velocity is defined as wavelengths divided by wave period. And when the phase velocity depends on wavelengths, then wave propagation is described as dispersive. And this is because if a wave of general shape were split into components of different wavelengths, the components would move at different velocities and thus become separated or dispersed. And dispersion equation relates wave circular frequency, sigma, with wave number and also the water depth. And this is the equation, which is dispersion equation. Wave circular frequency in power 2 is equal gravity multiplied by wave number multiplied by hyperbolic tangent, and under hyperbolic tangent sign we have wave number multiplied by water depth. If we substitute, instead of wave circular frequency, we will use 2 pi divided by wave period, and instead of wave number we will use 2 pi divided by lambda. We will get an equation for wavelengths, and wavelengths is defined as shown on this slide. So wavelengths would be equal gravity multiplied by wave period in power 2 divided by 2 pi n multiplied by hyperbolic tangent, and under hyperbolic tangent we have 2 pi d divided by lambda. As you can see in this equation, lambda is on both sides of this equation, on the left hand side and on the right hand side. So to solve this equation we would need to use iteration methods, or for example we can use solver function in Excel. If we divide both sides of this equation by wave period, so divided left hand side by wave period and right hand side by wave period, we get an equation for wave velocity c. Or if you take in power 2, you will get wave velocity in power 2, and you will get all this as shown in this equation. So you can see that the wave velocity depends on wave period and also depends on wavelengths and also depends on water depth. So this is it for today's lecture, and we continue in next lecture to consider physical principles of wave energy.